it's recorded here. So here we go. On Tuesday, for your class, we did not have time to actually go through and show how to graph a piecewise defined function, but I asked you to look at the video, and it was posted, I think, did I get that posted Tuesday night? But you had it all day yesterday you could have looked at. So hopefully you did that. We will do a little bit of review, though, for this. So let me get some folders out of the way. So take your Inspires and let's look at the problem that we have here. And again, we're looking at this function. Now this is a piecewise defined function, which means it comes in pieces, and we want to find on the Inspire the template that we're going to use in order to put in this function. So on this model, you've got a on the second key, the control with the multiplication. So if you do control multiplication, you've got the template palette. If you're on the other model, the black one, you've got really your own little key right here, and it pulls up the very same thing. Okay, so the black one, it has a key of its own. On the gray one, you have to do control multiplication. Now, we've got a couple of templates we could use, either one of these. The one that's highlighted right now is the one that is just for two pieces of the function. So we can use this one. However, let me just show you this, because occasionally we might have more than one, more than two pieces, and so we can choose how many pieces we want. Not necessary, okay, for us, but you could choose two and be right back to where we're going to be. So let me go back to my palette here and pick up two pieces. And we end up with that. Now, I forgot, I don't want it on the calculator page. Did you guys go to the calculator page also? You followed me here? Okay, let's just do delete. And what we need to do is pick up a graphing page. That's where I meant to be. But I've already shown you about that, so we'll just go ahead and use the palette. Now, you've got it in your notes, hopefully, but we'll kind of switch back and forth and see what we've got here. What's the first piece of that function? Yeah, and we have to make sure that we understand that the only domain, the only inputs that we can have for that piece are inputs less than or equal to 1. So I'm going to type in parenthesis x minus 1 and get outside the parentheses, raise that to the third power. There's the piece. And tab will get me over then to the domain. Okay, how are we doing? Good. And so I need x. Now I need x less than or equal to. On the touch screen that we have here, if you do control on the equals, you get a little template, a palette for this. If you're on the click pad, you actually have a symbols palette on this, it's called the catalog. So I do control on the catalog, and I get a more extensive list of these, and one of them is the less than or equal to. There's another way we could get to it, but I won't bother you with that at this point. And so it's x less than or equal to 1, and then tab, the second piece. Same thing, but squared. Okay, so we'll put x minus 1, and we will square that. And the domain to use for that piece is x greater than 1. I'll give you a moment to find all those. Doing okay? Okay. And we'll press enter, and there's our function. Now, you have to remember, this looks something like just a cubic curve, if you know what a cubic curve looks like, but it really is not. If we go to 1, this piece of it over here is a cubic curve. From here to the right is a parabola. So if you look at this, these are not truly symmetrical. They look kind of, but they're not. I'm going to change the window a little bit on this. I want to, maybe bring it to -4, and we'll go up to, let's say, +4, and that'll just give us a little more room. So to go to a window, go to Menu, go to Window, Window Settings, that's familiar with the 84, and let's see, I said what, -4, tab 4, tab scaling by 1, and I don't really need to have that decimal, so I'm going to make it -5, tab 5, tab 1. So we'll just do a little window like that. And when you're ready, just press Enter. I'll go down to OK and press Enter. And we have then, our work is there. Okay. The problem that we are to work on is find the derivative if it exists. And that's a big if for some of these. Now let's go back in our notes a little bit to this page. And what we have is what in some books is considered to be a theorem. We've got this: if it is differentiable, then it is continuous. And you have to understand, with these if-then statements like this, these are not reversible. This says that if you know the function is differentiable, then you can conclude that it is continuous at a certain point. If we look at our graph, we have to determine if it has a derivative at a point. Now, by looking at this, though, can you tell me if it's continuous?
I just have a question about that because I had to start over. Could you tell me how to get the last stand order?
On that model, if you do Control on the little catalog over here. Okay.
Thank you.
You're welcome. So is it continuous? Now, one thing we have to think about is the first piece is right over here. This first piece is a cube of a binomial, which when we expand it is just a polynomial. What do you know about the continuity of a polynomial function? Where? Everywhere. Continuous everywhere. So this function, this top piece right over here, we know it's continuous everywhere. What about the second piece? The one that goes with inputs greater than 1? Well, it's again, if you expand it, just a polynomial. So it also is continuous everywhere. Where is the only point that this could break down?
1.
At 1. It's the only point it can break down. Now, if it's continuous, then the value at 1 of the top function, the output value, has to have the same output value as the bottom function, the x minus 1 quantity squared. Let's test it and see. If I put 1 into this top function, 1 minus 1 is, cubed is 0. Okay. Now I can't use 1 down here on this second piece, but if I could put 1 in there, what would the output be? 0. Now, literally, this piece right here, when it gets to 1, it does not have a point there. If I were to graph this exactly just with the second piece, I'd have to have an open circle. Why? Because 1 is not included in the inputs. Okay, but when I get to this piece, I can use 1, and when I get to there, I have a closed dot, and that closed dot covers up the open dot. So is this function continuous through 1? Yeah. Okay, the output at this point, if we could use it, is the same thing as the output for this function. Okay, so we know it's continuous, but again, remember, that does not guarantee anything about continuity. This does not say if it's continuous, then it's differentiable. It says if it's differentiable, then you know something about the continuity. So be real careful about that statement. One of the examples I gave you was the absolute value function. And when we look at the absolute value function here, you know, we're looking at the slopes of the tangents, and the slopes of the tangents is the same thing as the limit. Now I'm going to do it this way. The limit as x approaches c, and that's going to be then looking at the slopes of the secants. Now, here's value c, right? There's my input c. You got to kind of stretch your mind on what a tangent is here and what a secant is. Basically, what we're saying is, what is the slope of the graph of the line tangent to all these points at this point, at coming up on this direction? And the slope is -1. If I were to put on this vertical axis the slope of the secant, I would have to come over here to 1, -1 actually, come down here at -1, and that would be then the graph of the slope of my secants. If I'm up here, the slope of my secants is up here at +1. Now you know about a limit, right? This is section 1.5. On a limit, you have to be able to come up from the less than side of your value and your greater than side, and your outputs have to converge. I often say you have to be able to clap. In this case, down here on the less than one side, your secant slopes are down here. On the greater than, you're up here. Can you clap? No. So we would say that this limit does not exist. When I take this limit, I'm actually looking at the derivative at c. So does the derivative exist? No. Why? Because the limit of those slopes doesn't exist. So we have to be real careful about this statement, especially when we then look at the problem that we're considering. So if we go over here to our problem, we'd like to say, well, we know it's continuous, therefore it has a derivative. No, no, no. That's not the way the statement's written. So what do we have to do? Well, we have to show that if I take the limit of the as the difference in the output, anyways, difference of the outputs of the difference quotient. I mean, in other words, take the limit of the secants on this side. So we're going to do this. Here's our work. From x less than or equal to 1, the slope of the tangents. Now, the slope of the tangents is what we're talking about as the derivative. The derivative is the limit as delta x approaches 0. You by now should be getting the picture what I'm going to write next. F of what? Yeah, x plus delta x minus f of x divided by, you know, nothing more than the slope. Okay, now we're only going to do this from one side. So the only function I can deal with is the top one, because I'm only dealing with the inputs less than or equal to 1. So I'm going to continue though, and this is going to be the limit delta x approaches 0. Now if I want f of x plus delta x, what's that look like? F of x plus delta x. All of that cubed. All I'm going to do is substitute x plus delta x in for the input here, minus what quantity? Yeah, just f of x, x minus 1, quantity cubed, divided by delta x. Now, chances are, and I think we talked about this, we don't, you know, I have it memorized because I've been teaching it for years and I work with it enough, but you probably don't have this memorized, how to cube a binomial, let alone how to cube a trinomial. This is why I give you this technology, okay? So we're going to use our technology to do this expansion. So go to Menu, Algebra, and Expand. Menu, Algebra, Expand. And remember, we're going to have to put our own parentheses in because we got a binomial here. So x minus 1, and get outside of the parentheses we put in and cube that. So it has to look like this. And we're going to press Enter. And there's our x cubed minus 3x squared plus 3x minus 1. Now, that's the piece that goes with this. Okay, that's this piece. What we have to do is to then put in our inspires, the trinomial. And instead of delta x, we're going to use h. And I'm going to do the lazy mathematician thing. Use an up arrow. Use an up arrow. I'm going to select it, press enter, and I'm just going to go in here and insert what I need. Okay? If you want to type it again, you're more than welcome to do so. And again, you can't use delta x. Many books use h, so we'll do that. And that, my friends, is what we have to put into all of this. Yeah. Did I? No, I think my work over here is wrong. Let's go back and check. Shouldn't that be a cube? Okay, because we're using the top piece. So thank you for correcting my work. Hopefully no one followed me on that, but we need to make that change. Okay, now what we have to do is limit delta x approaches 0. And I tell you, this is going to be almost impossible for me to write everything on the screen. Okay? Hopefully you can do a little better. We'll get all of our line out here because I've got to replace that entire quantity that I have over here. In place of h, I'm going to put delta x though. Okay? So while you are doing that with your work, I'm going to do it with mine, and we'll come back and check. So don't watch me up here. You should have it on your Inspire, and you can copy it as you need to. Okay, how you doing? I was being extra careful this time. In the class, I had an error up there, which wasn't bad. I like making mistakes in front of you because then it's a chance to tell you what you need to be watching out for also. But let's see what we've got here. At this point, if we did this carefully and correctly, what should I be able to do? Not yet. In the numerator. Yes. Cancel every term that doesn't have a delta x in it. Now, I'm not going to go back and rewrite this, I can tell you that. But look at this. I got subtracting this whole quantity. I've got to keep in my head, keep track of the fact that this is negative, change the sign positive, change the sign negative, change the sign positive. But let's see. Here's an x cubed. Do I have a negative x cubed? Yeah, right there. Okay. Here is a negative 3x squared. Do I have a positive 3x squared? Yes. Okay. And here is, there's a problem now, isn't there? I've got a negative 3x. I need on this quantity, and here I need a positive 3x. I think I know what I did wrong.
It's supposed to be 3x plus 5x.
I think, let me go back. I was thinking this was supposed to just be 3x there. And well, that's just...
3x comes before the x.
Okay. So let me see. I'm moving my cursor. Tell me when to stop.
Stop there.
There it is. Yeah, I combined those, didn't I? Did the same thing in the other class. Okay. So I need to put a plus in here. Yeah. Forgot that. Okay. I knew that there was a mistake, okay? Because I know where I need to go. It's okay to make mistakes. I think my golfer is gone today, right? Here? Okay. In my experience, I'm taking golf lessons and all this stuff. If you're baseball, basketball, playing a musical instrument, whatever, it's the same thing. But I was told that in all these lessons, my lessons in golf isn't going to make me do better good shots. I just make less bad shots or less imperfect bad shots. My bad shots aren't as bad as they used to be, okay? I still make bad shots. Just like with this, we still are going to make arithmetic errors or transposing number errors or whatever. It's just because we're human. But if you know you made the mistake and you have a way of finding out, that's the more important thing. So I knew that somewhere I had a mistake because I need to be able to cancel those out. Use that as a way of checking your work. Here's a negative 1. Is that going to be a positive 1 here? Yes. Okay. Now, the next step then, after all of those are factored out, the next step then is to be able to do what? Yeah, if all of those terms left have a delta x, then I should be able to factor out a delta x. Go back and do the work. Make sure that you've got all those terms. Now, when we get done with this section, we're never going to do limits, derivatives this way again. But we have to finish this up because we have to know why those rules work. And then it's Dylan, right? We're going to answer Dylan's question he had Tuesday. He is excited to know where he's going to use this information. And I'm excited to show it to you. Because really, this stuff, who cares? I agree with you, Dylan. I don't walk out of here and do this work. But I do walk out of here and apply derivatives. Okay, so I'm really excited to get to that part, but we have to kind of learn the basics, as I said on Tuesday. Okay, so now I can cancel the factors, and now can I make the substitution? Yeah, I couldn't before because why? And why don't we like that in the denominator when delta x is going to 0? It's an undefined value. Okay. So we end up then with, what is this? 3x squared minus 6x plus 3. Now, the problem with doing the work is you get all this done and then it's like, what was the problem to begin with? I don't know. I forgot where I was going on this. So let's review. What is this? Derivative. Yes, this is our derivative, but it's the derivative for x less than or equal to 1. Okay, let's test it out. Let's suppose, okay, so if x is equal to, let's say, -1. So I have the derivative of -1, and I'd have, 3 times -1 quantity squared minus 6 times -1 plus 3. Negative there. There we go. Plus 3. -1 squared? 1. 3 times 1? 1. -6 times -1? 6. 3 plus 6, 9. Plus 3 would be a 12. That's otherwise known as the slope of the tangent. Let's go back to our graph. Menu. We're going to put a point on. We're going to put a point on here. What coordinate do I want on that point? -1. There we go. Can't see the point, so I'm going to change the window. I can go back in and do the window as I showed you, or I could, let's see if -10, I'll just change that. There it is. I just changed that number. Same way we change all this text, just double click. Okay, so I'm going to go in, put a tangent on there. Now, at some point, hopefully you guys will feel comfortable doing it also. I mean, we've done this enough. If you can't keep up with me, at least you can imagine yourself doing this work. Menu, measurement. We're going to measure the slope of that line. So the slope of the secant is 12. What's going to happen if I grab that point and bring it up closer to 1? Slope's going to change. Okay? Slope is going to change. Now, we haven't finished the problem on our notes yet, though. Because all we're doing is we're saying that if I have this point and I have it over here, now if I grab that point and bring it up closer, by the way, did our slope match what we had analytically? Okay, so if I bring it up and bring it up closer there, I need to know what happens as I get closer and closer to 1. That's the discussion. So here we go. I'm not done because all I've done is to work with one side of this problem. What we have to now do is say for x greater than 1, and we got to go through this whole thing again. Okay? Because now if I'm going to be greater than 1, I've got to do it for this piece. Remember, this function's different on the right-hand side than on the left-hand side. So now I need to look at the slope of the tangent. I'm going to kind of work through this. Hopefully you'll keep up with me. I'm just going to go through this whole thing again. F of x plus delta x minus f of x divided by delta x. Only this time my function is x minus 1 quantity squared. So I've got the limit delta x approaching 0. I've got to put in x plus delta x minus 1 and square it, minus x minus 1 and square it, and delta x. I've got to do the very same thing I did. I've got to expand, okay? But again, this is why we have this technology to you. I don't need to go up and redo a whole bunch of stuff. I just need to go up, copy it. Whoops. Before I do that, let me erase everything. Yeah, my mouse here. There we go. Okay. So, you know, go up, copy that command we want, bring it down. The only thing I'm going to change is that exponent. Okay, that's all I have to think about. I come over here, I'm going to have the limit, delta x approaches 0. And let's see, you guys can work on your page there. I've got this up here. If I make a mistake, we'll find it. Let's see. Look over here. Can I get that all? Minus delta x plus 1. And then I have to subtract this one, we all know. And again, I'm looking for terms that I know are going to cancel. If that doesn't happen, I know I just have to go back and check my algebra. Kind of repetitious, isn't it? Okay, when you get to the point where it feels like it's repetitious, you know what? You got it. You got it. You know how to do the problem. If they begin to look like not new problems, but just the same thing, but different numbers, you got it. Okay, so now we end up with 2x minus 1. That doesn't look anything. Did I drop a 2 someplace? Okay, that doesn't look anything at all like the first one we did, but this is the derivative as x is greater than 1. Okay, so let's say for x, let's say x equaling 2, the derivative is going to be 2 times 2 is 4 minus 1, or 3. We'll test it out. I know I'm working a little bit fast here. I want to make a point on this. What did I give myself a point of what? 2? Was it? I think it was on that. On my notes. Now, there's the point 2, 1. Now I need to go back, do the tangent again, but at this point instead, we're going to measure the slope. What did I say the slope was? I got a mistake, don't I? Yeah, got a mistake. This is a way we check our work. Now, my slope that I get here should be the same thing. And I actually said this wrong. This is the slope of the tangent, not of the secant. Okay, so now, where's my mistake? It seems like This should be a 2x minus 2. Where did I make the mistake? So up here, that should be a 2? Okay, there we go. Now, how would I have known that? Well, just the same way. I checked my work, okay? I know the slope of the tangent on the graph should match what I have here. Now, does it match? Yes. My analytical work doesn't have to be wrong as long as I can make sure that it's, matches up there. Okay, now let's see. I've got the slope of this one. As I bring this point closer and closer to 1, where's the slope of this tangent going? And if I bring this point closer and closer to 1, where's the slope of its tangent going? Are they going to the same thing? Are the tangent slopes going to the same thing as I come up on both? Isn't that what a limit says? Come up on both sides. They should be going to the same thing. So you can clap. It's working. Okay? So let's go back to our work here. Do we know whether or not, and the question was, does that derivative exist? And if so, what is the derivative? Well, the derivative actually could be either one of these equations, but I would more likely have it be this one because it includes the value 1. Okay? It doesn't include the value 1 down here. But the derivative does exist. And in fact, what is the numerical value? What is the slope of the tangent at 1? How would you do that analytically? I want to know the slope of the tangent at 1. And we found that they converge, okay? So if I put 1 in here, I've got 3 minus 6 plus 3, which is 0. Let's make sure they converge, though. So if we could use 1 over here, which we can't, but if we could, what is the derivative? Well, let's see. It's 2 times 1 minus 2, or same thing, right? We found it analytically. We see it graphically. Okay? Now, I've done a lot of button pushing here. You guys are doing well, though. I could tell from the quiz we last took. Don't be intimidated by with the technology. If you don't want to use the Inspire to do all this stuff, you don't have to. But you do have to show me graphical work. Okay? That pretty much finishes up then section 2.1. The next thing we do is just, I'm going to skip that stuff, and so we're done with section 2.1. Okay,